bachelor student, second year of education as a helper, that grown in the bachelor and master's thesis, which were dedicated to the photodynamic therapy with the 60 fullerene. And later on, we together developed the idea of a PhD thesis, which was then realized at the Professor Markus Fromme group with the support from DAD, German Exchange Service. And that time I got also very good help and support from Professor Olga Matuszewska. So my deepest gratitude, and it's my biggest pleasure to introduce Professor Olga Matuszewska with the talk, Photodynamic Cancer Therapy with Carbon Nanoparticles.
And one word to add, I'm really grateful that I could inherit Anna.
Anna is my beloved student, it was my beloved. Dear colleagues, first of all, I would like to thank the organizers for inviting me to give this lecture for young scientists. And it's more a pleasure because fullerene C60, which is the representative of carbon nanoparticles, united the scientists from Ukraine and from Germany. And this lecture will include the data obtained both in Taras Shevchenko University, Palladium Institute of Biochemistry of Academy of Science of Ukraine, and German universities, Technical University of Illinois and Technical University of Wilhelm. So let's to begin with, I choose several states from the scientific published manuscripts, which I use like an epigraph to my lecture. The first is, an ideal vision of modern medicine includes anti-cancer treatment with the human body remaining completely intact. And even though there are many different types of cancers, the only thing they have in common is their susceptibility to induced cell suicide. So what is photodynamic cancer therapy? It is a novel, non-invasive or minimally invasive clinical treatment utilizing photosensitizers in conjunction with a specific light aimed at local destruction of cancer cell by generating excessive cytotoxic reactive oxygen species. PDT has three functional elements: light of specific wavelengths, photosensitizer, and molecular oxygen. Taken separately, none of these elements work. But when they are combined, they have a toxic effect against cancer cells. It is hard to speak about photodynamic therapy without a short excursion to history. And we will see that it is indeed a very ancient case, and we will find two Nobel laureates in 20th century. So, 3,000 years ago, Egyptian people used a combination of the orally ingested Magus plant, is some kind of parsley, well-known plant which we use, and sunlight to successfully manage vitiligo, a skin disorder of unknown case. The active ingredient of this plant, psoralen, is now successfully employed in worldwide treatment of psoriasis. So here we can see the consequences of this disease. This is the plant, and this is psoralen, and I would like to put your attention on the system of deconjugated double bonds in this structure, because forward we will see this structure often. In 1903, Nobel Prize in Physiology was awarded to Dennis Finsen from Denmark in recognition of his contribution to the treatment of diseases with concentrated light rays. Finsen demonstrated phototherapy, and it was his therapy, phototherapy, for treatment of skin diseases by a carbon arc lamp in which ultraviolet rays were filtered off by red glass, the Finsen lamp, thus preventing irritative effect on the skin. And Finsen established the first medical light institute in Denmark. Let's go on. The early 90s. The birth of the photosynthesitis hematoporphyrin. It was extracted from the blood by removing iron. And it was the first experiment with a patient, because German scientist Meyer Benz injected himself with the group hematoporphyrin and experienced a signal general skin sensitivity upon exposure to sun for 2 months. It was shown also that after hematoporphyrin injection in animals, the accumulation of significant fraction of dye is in primary tumors, and PDT efficiency were demonstrated. And the second Nobel Prize, it was awarded to Hans Fischer to clarify the structure of the porphyrins. It was really a great progress, because the photoactivity of natural products was known, but its exact detailed structure was unknown. And Hans Fischer showed that the all porphyrins contain 4 pyrolyl rings, in which carbon atoms are bound to single bonds and one double bond, and this sp2 hybridized. Fischer synthesized this structure, which is not known to a chemistry, named porphyrin. And the most photosynthesizers, even modern synthesis, are derived from this tetrapyrrolic structure. During this year, it was shown that the hematoporphyrin derivatives, their effect is higher than the effects of hematoporphyrin himself. And other studies culminated by the synthesis of photophyrin. This is the first photosynthesizer given approval of United States Food and Drug Administration for use as a photosynthesizer in clinical practice. This is a short history, but since the porphyrin and their drivers are used in clinical practice of very different cancers, cutaneous, subcutaneous cancers, digestive, lung, uterus, breast cancers, it problem needs a new method. Now let's tell a few words about how photodynamic cancer therapy is realized. It is a two-stage process. At first, photosynthesizer is given to a person, for example, applying to the skin, or by mouth, or by injection with a needle, and in this case, it's the only puncture made to the organism. The photosynthesizer is accumulated during approximately 24-72 hours. It is difficult to visualize it in a human body, but here is the picture made with fluorescence imaging with the use of the porphyrin derivative as a photosynthesizer and the organoplatinum metal cage. And it is very well demonstrated how the photosynthesizer achieves the body and is concentrated in the human tissue at 20 hours. The next step is light radiation. It also applied depending on the tumor localization. It could be directed to the skin, for example, if it is throat or digestive system or lung, then use an endoscope. And now the optical fibers exist, the size of which allow to introduce them even in the small capillaries. What is the problem with photoexcitation of photosynthesizer? It is the relationship between wavelength of light and skin penetration depth. You see that the blue region allows to penetrate approximately to 1-2 centimeters, while approximately to 5 centimeters allow to penetrate red illumination. Now, different labs, dyes, lasers to realize the ETG. The photosynthesizer is left the normal size, approximately 72 hours, but it is accumulated at a period typically several months or even years. The selective destruction of tumors take place, and during this period the patient had to avoid sunlight. And what is the good feature of photodynamic therapy? No resistance to procedures. It can be repeated for several times. Of course, every drug has some disadvantages, and the disadvantage of photosynthesizers based on porphyrin structure are for other complex composition, no tumor specificity, rapid degradation in organism, unavoidable absorption spectrum, and high toxicity. That is why new generation of photosensitizers are not being developed. And nano materials, carbon-based nanomaterials, are preferred because of the superior optical properties, mechanical stress, biocompatibility. Here we can see the carbon-based nanomaterial for the non-photodynamic application. Carbon nanotubes. Carbon nanotubes can absorb the light in infrared region, 1,000, 100, 1,200. And that is why they are heated. So they can kill the cancer cells, but because of this thermal effect, they can kill also the normal cells. And their bioavailability is poor, so they rather are used for transporting some drugs, or they can be functionalized with photosynthesizer. Graphenic side. Graphenic side is useful because it has a great surface, and it also can be functionalized with drug, for example, with photosynthesis. It is more biocompatible, but it also shot light in the region of 800 nanometers, and it also is heated. It is used to grow the bones on the surface of the graphenic side of the drug. The drug is released, and the graphenic side can transport it inside the cell. But the absorption optimum is not good. Quantum dots. Quantum dots are the rising star for bioimaging because they are a little less than 10 nanometers, and they have a very huge fluorescence. And you can visualize the traffic of quantum dots even in the body. And I think that these nanoparticles have a future, but they are photoexcited only under low ray, X-ray radiation. And now is our beloved object, 60. It has unique properties because it is hydrophobic, experimental, symmetrical, approximately 1 millimeter in diameter, and 60 carbon atoms won't form a ball-like atom cage, and that is sp2/3 hybridized. What are the features of fullerene is possible photosynthesis? Fullerene is the only between those nanoparticles about which I told you. With the only who absorbs, which absorbs light in the visible range. Also, it is shifted to a blue range to ultraviolet. C60 has high photostability and resistance to photobleaching. Photoexcited C60 efficiently generate reactive oxygen species, and the quantum yield is nearly 100%. It's very high. And there are reports that PDT with fullerene can destroy subcutaneous tumors in mice. This is experiments in vivo which are rather rare. The mechanism of photodynamic therapy with fullerene C60. Normally, this nanostructure is in the ground secret state. After softening of a quantum light energy, it is photoexcited and go to excited single state. It is short-lived, very short-lived, 2 nanoseconds, but it can either transfer to triplet state with a more period of life. And what is the advantage of fullerene? Most photosynthesizers after exciting go back to the ground single state, but not fullerene. The energy of fullerene is for the excited triplet fullerene can be used in 2 types of photochemical reaction with produce of reactive oxygen species, but singlet oxygen, superoxide anion, hydroxyl peroxide, and hydroxyl radical. Between them, superoxide anion is rather weak oxidant, and it can't transpose through the cell barrier, but it is used in reactions to generate other reactive oxygen species using this reaction. For example, hydroxyl. The most toxic of them is hydroxyl radical. The period of life is rather long, and it easily penetrates cell membranes, and it can easily diffuse to the tissue among the cells. So we use in vitro experiments this exciting structure, and the goal was to choose the cells. It's very important for biological studies. What kind of cells do we use? What is the dangerous and what is the problem? As you have seen, fullerene needs the presence of oxygen to realize his phototoxic mechanism. But the solid tubes, they are hypotoxic inside especially, and this mechanism couldn't work. So, choosing the orbit, the cell line, we use the leukemic cells. Why? Well, first, because you know leukemia is a very serious type of cancer, very highly treated. And the second reason was that there is a special method which is named electrophoresis, ESP, to treat leukemic cells in patients with blood cancer using their blood, where the concentration of oxygen is rather high. It can be transferred to the in vitro experiment where also the oxygen content is enough. So we used in, what is the idea in short of this method, ESP? The blood is collected from the vein, then the lipocytes are isolated with a special device. They are irradiated and by ultraviolet A and in the presence of fluorescence reserve, and then the person is rain infused. This method is widely used in clinical practice. So we use in experiments in vitro as a model of leukemia, human cancer T cells for glucose and C7 and mouse lymphoid leukemia cells, L12. Another need is to have a good preparation of fluorescence 6. And it was due to our collaboration with Peter Schaff Laboratory in the now Technical University. They have a very nice method of purification fluorine with gas chromatography, and it's fast transfer from toluene to water solution. So we get the colloidal solution, fluorine colloid water solution, and with very good parameters for purity, pure concentration of the hydrogen minus 4 moles per liter, average nanoparticles diameters 50 nanometers, and by analysis with laser correlation microscopy, we have shown that this diameter was not changed in time during measurements. High stability also is very important. This water colloid solution was stably more than for 1 year at appropriate temperature storage. First of all, what we've done, we have to be convinced that the fluorine is accumulated inside leukemic cells. Fluorine doesn't have its own fluorescence, and so it is impossible to visualize its traffic inside cells. So we use the fluorine labeled with fluorescent dye treats. And in this picture, you can see that it efficiently enter cells through 2 hours, and at 18 hours, most all of cells have this nanostructure, fluorine. What was the conditions of intracellular C60 photoexcitation? Taking in account the absorption spectrum of fluorine, we use the diagram. The emission spectrum was in the visible diapason, and from 400 to 600 nanometers, 2-minute duration. The scheme is cells were pre-incubated with fluorine and then irradiated and further incubated. It is important to use to estimate the viability of cells after this process. And more or less important is to use normal cells to combat the effects. And we use also normal cells, tumor cells. And it occurs that tumor cells do not feel any procedures and any toxic effects, while Jucan and delta cells viability is decreased. Is this phenomenon is caused by ROS production? Yes, it is, because we use the DCF dye, specific for ROS, inside the cells, and both Jucan and L10 cells are shaped by dramatic increase of ROS, but thymostrate do not. what would mean the cells lose their viability and are killed by photoexcited fuel? You see, Jurkat cell is origin from the peripheral blood of the 14-year boy who has leukemia, this cell-like Jurkat. And they efficiently absorb and accumulate sugar, and we were glad to see that after 24 hours, no effect with fluorine separately, with irradiation separately, and this is a combination. And we also determined that the cells lose their viability because of cell death by apoptosis. It is the mechanism of transmission. We demonstrated by electrophoregram that Jurkat DNA has typical ladder pattern with these fragments present, and the executive enzyme of apoptosis displase 3 is also activated in 24 hours after radiation. What is another agent problem in photodynamic therapy? You know it very well, I think. It is the resistance of cancer cells to chemotherapy. And we wonder if we can modulate this resistance in the use of the deposition. In this experiment, we use two kinds of cells. This is sensitive to anti-cancer drugs, and this is resistant. They even on their morphology. And they differ in their sensitivity. You see that normal sensitive cells die even at 1 microgram, while no answer of resistance that we can observe. So, what are the results of combined treatment with photoexcited C6 and this blood? We were glad to see that photoexcitation of fluorine has a toxic effect on resistance to these plasma cells, you see, radiates. And I will say once again that there is no resistance to this prostitute of photoexcitation, to PDT. You can combine it with other means and you can repeat it. And combined of C6 radiation and this blood allow to restore the sensibility of resistant cells to the drug. And what is important, to restore the sensibility to drug in a rather low concentration. When Anna Rybin was our student, a master student and then PhD student, she has a very exciting idea. The case is that really we need now a new generation of photosensitizers. They have to be more efficient. They have to have a more sharp spectrum, be portable, and be of a low cost. So our idea was to use light-emitting dyes with a specific wavelength. It was her idea, and she successfully realized it when she was a PhD student at Bilbao University. What kind of LEDs were used? Those who have an emission spectrum in diapason which are overlapped with 60 fluorine absorption. This is 355 violet LED, then 45 nanometers blue one, and 515 nanometers green one. What are the results? Of course, the most pronounced toxic effect after photoexcitation of fluorine was with the blue 165 nanometer diode. You can see that the cells dies even at low light fluids, for example, 2%. But the toxic effect was observed also without fluorescence. It was the toxic effects of this toxic ultraviolet diodes. From the other side, no toxic effect was seen on cells when we use green LED, but no effect with combinations. So here is the optimum where when the ability of cells which are decreased negligibly, and the effect of photoexcited fluorine is rather massive. So we have the instrument to photoexcite fluorine, but is this structure really penetrate the cell membrane and is accumulated inside the cancer cells, and where it is accumulated? I would like to emphasize that AMMA used in this experiment CCRF cells as human leukemic cells. And if in previous experiments we used fluorine labeled with Ritz fluorescent type, in this experiment the FITs labeled antibodies to fluorines were used. They have green color inside the cell. And DAPI, which is used to mark the nucleus of the cell. And which is a very nice picture, I like it very much, because it demonstrates that fluorine really penetrates through the plasma membrane and is accumulated in the cytoplasm, in the extranuclear location, not in the nuclear. If to say about other experiments, further it was shown that in cytoplasm fluorine are accumulated in mitochondria. So if in human leukemic cells this structure is accumulated, maybe it is also because of the Ross generation. And here is the picture where the level of reactive oxygen species is estimated. You see that it is rather high 3 hours after the manipulation. And there is a specific fluorescent label for Ross, it is DCF. And you can see that in dark, no effect is visible, while after radiation with the lead 405, we see a huge loss production, maybe even a loss oxidative stress. Again, the question appears, what kind of cell death is it in this case? And here was used a very informative method with double mixin fits the propygium staining, which allow to differ between the viable cells, necrotic cells, and apoptotic cells. And you can see that when in dark, no effect is visible. Then at 6 hours, the number of early apoptotic cells increased, and at 24 hours, the number of late apoptotic cells is rather high. But it's important that the number of necrotic cells was not changed during viscosity. So it is really self-suicide was demonstrated after photoexcitation with light emitting diode. So I hope that I convince you that Fuller 60 is a perspective photosynthesizer PDT, and this field needs newcomers to the field, because it's possible to modify fluorescent surface with fluorescent antenna, with specific ligands to receptors on cancer cells surface, or with enzyme, and it's very interesting constructions which are done nowadays, and wait for its application and for its estimation for clinical application. I would like to thank a lot to my colleagues, Dasha Franskevich, Svetlana Predluska, Irina Hremenko, Professor Yulia Krylowski from Kyiv Shevchenko University, Ludmila Drobat from Paladin Institute of Biochemistry, Professor Verita from Technical University of Leningrad, Anna Hrebinik and Marcus from Legal Technical University. Thank you for attention. I'm ready for your question. Yes, please. Yeah, you're welcome.
Thank you for the great presentation. I would have quite a few questions. Like one question is, you can chemically modify fullerene, right? But how much does it change the properties of the fullerene? Because I could imagine it has a lot to do with the symmetry. And at the moment you modify it chemically, you break the symmetry, maybe the triplet yield decreases, and I don't know what. So
you are absolutely right, absolutely right. And that is why when the fields labeled antibodies to fullerene were used, it is more exciting and more modern method. But the cost of antibodies is rather high, antibodies to fullerene, and we can't use it, and so we have labeled fullerenes with reeds. And of course, to some extent, it's modified its surface and maybe its properties, not penetration inside the cell, and maybe activity and the ability to be photoaccepted. I don't mention in my lecture the fact that we use crystal fullerenes, not modified. Why? Because of course, functionalization of surface of fullerene improve its solubility and increase its hydrophility, but it also destroy this p-conjugated system with this hybridated bonds. And we were glad to convince us for all of those who are in this problem that crystal non-modified fullerene is a perspective. If it used as a stable colloidal solution, very stable for 1 hour. So we believe in it is perfect. Thank you.
More questions?
Is it possible to use a photodynamic cancer treatment for another types of cancer, not only leukemia?
Yes, of course, and there is a lot of manuscripts which describe the localization of fullerenes in tumor. But what is you see, one way is to make in vivo the whole organism and only to visualize the traffic. And the other case is to examine the biochemical mechanism. Then you need cell lines in vitro. And in cell lines, of course, you want to be near the in vivo situation, like it is in the cancer. And the cancer cells are in the blood, and it's a very dangerous and very popular cancer disease. But of course, it can. The first fact when the photodynamic therapy efficiency was improved was with the using of a mice with subcutaneous tumor, and it really disappeared after injection of crystal fullerene and its photoexcitation.
Naturally based
Is anyone works with
Cloud,
liposomes? Is anyone works with the natural-based nanoparticles as liposomes in your university or institute?
In our group, we were concentrated in soluble donated fluorines, but to include it into liposomes, it's another way to use it. And if to compare, for example, the presence of these forms of drugs and of fluorines in the market, the first place is the liposomes form. It's widely used, but it has some disadvantage I would like to talk about it.
You don't know somebody from Ukraine, yes, who works in this direction.
Do you know somebody from Ukraine who works with liposomes?
fluorines?
With liposomes.
Is liposomes, of course, please. I can invite you to the Institute of Biochemistry, Poland Institute of Biochemistry. They use liposomes and they studied them carefully. So.
I will talk to you later.
I don't hear what you say.
She will talk with you later.
Okay.
So networking is taking place. So is there any more questions? Please.
Can this approach replace chemotherapy? Can we use some photodynamic without use other treatment?
Without using the drug, yes? Of course, and my lecture was about this kind of specific application you can use. And the case about which I have said that the subcutaneous tumor of mice was disappeared after fluorine co-excitation without any drugs. But it's another problem, and it's another lecture maybe. Anna also is engaged in this theme. It's a combined action of fluorines with doxorubicin, with berberine, for example, when these drugs are covalently or non-covalently conjugated with fluorine. Then the efficiency, of course, is increased in this very perspective. And if you also, for example, introduce the red antenna, or ligand specific to receptor of cancer cell, then the effect will be even more higher.
Is there any more question?
Okay.
So it seems we're very good in time.
Very good.
Thank you.
Okay. Thank you very much. So, now networking and drinking. Science at the bar, part 2. You know the location. If not, find it on Vuva. It's not far from here. And I think somebody will walk in front and you just follow if you don't know.
You follow
Right.
us, let us either in 5 minutes downstairs.
Yeah.
And please, who is presenting today? Let's gather and please transfer to me your presentation.